Imagine for a moment that you're standing on a beach at night, looking up at a sky littered with stars, and you let yourself ask the question that every curious mind eventually asks, is time travel possible? Not the movie version, not the time machine with spinning dials and flashing lights, but the real thing, a genuine journey into the past or the future, permitted by the actual laws of physics. It's a question that sounds like science fiction, but here's the astonishing truth. Physics doesn't rule it out. In fact, one direction of time travel isn't just possible, it's already been done, measured, and confirmed in laboratories and in orbit above our heads. The other direction is far stranger, far more speculative, and takes us to the very edges of what we understand about reality. So let's take this journey together, slowly, the way any good exploration of the universe should go, starting with a question that seems simple but turns out to be one of the deepest rabbit holes in all of science. What exactly is time? For most of human history, time felt obvious. It ticks forward at the same steady pace for everyone everywhere, like a great cosmic drum beat that the whole universe marches to. Isaac Newton believed this. He imagined time as an absolute stage, ticking away in the background, indifferent to whatever was happening in the foreground. A minute on Earth was a minute on the moon, was a minute on some distant planet orbiting a distant star. This picture felt so natural that nobody thought to question it for more than 2 centuries. And then in 1905, a young patent clerk in Switzerland, a man who couldn't get an academic job, who was considered something of an outsider, sat down and dismantled that comfortable picture entirely. His name, of course, was Albert Einstein, and the theory he produced, special relativity, changed our understanding of time forever. Here's the key insight, the one that started everything. Einstein realized that the speed of light is the same for every observer, no matter how fast they themselves are moving. That sounds like a small technical detail, but it's actually a wrecking ball aimed at our intuitive notion of time. Think about it this way. If you're on a train moving at some speed and you throw a ball forward, someone standing on the platform watching you will see the ball moving faster than you do, because your speed and the ball's speed add together. That's ordinary common sense, and it works for balls, bullets, and baseballs. But light doesn't play by those rules. If you shine a flashlight forward from that same train, someone on the platform will measure the light moving at exactly the same speed as you do. Not faster, not slower. The speed of light is locked, fixed, non-negotiable. For that strange fact to be true, something else has to give. And what gives is time itself. If 2 observers moving relative to each other must both measure light at the same speed, then their clocks cannot be ticking in sync. Time, Einstein showed, is not an absolute river flowing at the same rate for everyone. It's flexible, it bends, it stretches and compresses depending on how fast you're moving relative to someone else. This is called time dilation, and it's not a mathematical curiosity. It's a measured, verified, everyday reality. Astronauts on the International Space Station age very slightly slower than people on the ground because they're moving so fast around the Earth. It's a tiny effect, mere microseconds, but it's real. And it's been measured with atomic clocks precise enough to catch it. And here's where the story gets even richer, because Einstein wasn't finished. A decade later, he extended these ideas into general relativity, and this time, gravity entered the picture. Einstein showed that gravity isn't really a force pulling objects together in the way Newton imagined. It's the effect of mass and energy warping the fabric of space and time itself. Picture a stretched rubber sheet with a bowling ball placed in the middle. The ball creates a dip, a curve in the sheet, and anything rolling nearby will curve toward it. Not because some invisible hand is pulling it, but because the geometry of the sheet itself has changed. That's gravity, according to Einstein, the geometry of space-time bent by mass. And this bending doesn't just affect the paths that planets and light take through space, it affects time too. The stronger the gravity, the slower time ticks. A clock sitting near a black hole runs slower than a clock far away from any gravitational source. This isn't speculation, it's been confirmed again and again. And in fact, your GPS satellite in the sky right now has to correct for this effect, because clocks in orbit tick at a very slightly different rate than clocks on the surface, thanks to both their speed and the weaker gravity they experience. If engineers hadn't built in Einstein's corrections, your GPS would drift off by miles within a single day. So already, before we've even gotten to the exotic stuff, we've established something remarkable. Time travel into the future is not only possible, it's happening constantly in small ways all around us. If you move fast enough, close to the speed of light, or if you spent time near an object with immense gravity, like a black hole, you would experience time passing more slowly than people far away from you. Come back after your journey, and you'd find that while only a few years passed for you, decades or even centuries might have passed for everyone else. That is genuine time travel into the future, permitted in principle by the very same equations that keep your phone's map accurate. But forward time travel, however strange it sounds, is really just a matter of degree, an extension of the fact that clocks tick at different rates depending on speed and gravity. Backward time travel is a different beast entirely, and it demands we take Einstein's equations and follow them into much stranger territory. That territory involves an idea you may have heard of: wormholes. Here's how the idea works. If space-time can be curved by mass and energy, then in principle, it might be possible to curve it so dramatically that two distant points become connected by a shortcut, a tunnel through the fabric of the universe itself. Imagine folding a piece of paper so that two far apart points touch, then punching a hole through both layers. Instead of walking the long way across the paper, you could step through the hole and arrive instantly. That's the basic idea of a wormhole, a bridge connecting two regions of space-time, potentially even two different times. The mathematics of general relativity does technically allow for such structures. Physicists call them Einstein-Rosen bridges, named after Einstein and his collaborator Nathan Rosen, who worked out the equations describing them back in 1935. And there's nothing in the mathematics that strictly forbids one end of a wormhole from connecting not just to a different place, but to a different moment in time. If you could construct such a thing and keep it stable, you could, in principle, walk through one end and emerge from the other end in the past. This is the closest thing physics has to a genuine, mathematically grounded time machine. But, and this is a big but, there are ferocious obstacles standing between the mathematics and the reality. First, wormholes, as described by the raw equations of general relativity, are wildly unstable. The moment anything, even a single photon of light, tries to pass through, the wormhole tends to collapse and pinch shut faster than anything could cross it. To keep a wormhole open long enough for something to travel through, you would need what's called exotic matter, a form of matter with negative energy density, something that essentially pushes space-time apart rather than pulling it together. We know from quantum physics that tiny amounts of negative energy can exist in very specific and fleeting circumstances, but producing and sustaining enough of it to prop open a tunnel through space-time is, as far as we currently understand, wildly beyond anything we know how to engineer, and it might not even be possible in principle. So a wormhole time machine remains, for now, firmly in the realm of theoretical possibility rather than practical engineering. There's also a deeper philosophical thicket waiting for us here, one that has occupied physicists for decades. If backward time travel is possible, even in principle, does that open the door to paradoxes? The most famous of these is the grandfather paradox. Suppose you traveled back in time and prevented your own grandparents from ever meeting. If they never meet, you're never born. But if you're never born, you can't travel back in time to prevent them from meeting. It's a logical loop that seems to eat its own tail. Physicists have thought hard about this, and there are a few fascinating proposed resolutions. One is the idea that the universe's laws might simply conspire to prevent paradoxical actions from ever succeeding. This is sometimes called the Novikov self-consistency principle, after the physicist who proposed it. In this view, if you traveled back in time, you would find that anything you did was always already part of history. You couldn't prevent your grandparents from meeting because history already accounts for whatever you do. Your actions become woven into the fabric of what already happened rather than something that changes it. It's a strange, almost fatalistic idea, but it's mathematically consistent. Another proposed resolution invokes the idea of multiple branching universes, the notion, inspired by certain interpretations of quantum mechanics, that if you traveled back and changed something, you wouldn't alter your own timeline, but would instead split off into a new branch of reality, a parallel universe where events unfold differently. In that picture, there's no paradox at all, because the you who changes history is not erasing the original timeline, just creating a new one alongside it. It's a beautiful idea, deeply strange, and it remains speculative, tied to interpretations of quantum theory that are still debated. Now let's pull back and ask a broader question, because time and space in this story cannot be separated from where all of this, space, time, matter, energy, actually came from. That brings us to the Big Bang, about 8 billion years ago, as best we can tell from mountains of observational evidence. The observable universe was compressed into an extraordinarily hot, dense state, and it has been expanding and cooling ever since. This isn't a story of some explosion happening at a point within an already existing empty space. Rather, space itself has been stretching, carrying galaxies apart from one another the way dots drawn on the surface of a balloon move apart as you inflate it. The light that reaches us from the earliest moments of this expansion, the cosmic microwave background, is essentially an afterglow of that hot young universe, and its detailed patterns match theoretical predictions with breathtaking precision. Here's what makes the Big Bang relevant to our story about time. If time itself, along with space, emerged from this event, then asking what happened before the Big Bang might be a bit like asking what's north of the North Pole. It could be a question that doesn't quite make sense within the framework we're using, because the very notion of before, which depends on time already existing, might not apply to a state in which time itself was coming into being. Some approaches to quantum gravity suggest there might have been a before, perhaps a contracting universe that bounced into an expanding one, or a broader landscape of universes bubbling into existence. These are active, unsettled areas of research, genuinely at the frontier, and nobody should pretend we have final answers. But what's certain is this: the origin of the universe is bound up with the origin of time. And that reminds us that time isn't some backdrop that was always simply there. It's a feature of the universe, as physical and as changeable as space itself. This brings us naturally to string theory, one of the most ambitious ideas in modern physics, and one that tries to unify everything we've talked about, gravity, quantum mechanics, the behavior of matter, into a single coherent framework. The core idea of string theory is deceptively simple. Instead of picturing the fundamental building blocks of nature as point-like particles, imagine them instead as tiny vibrating strings, far smaller than an atom, far smaller even than the particles that make up atoms. Different vibrational patterns of these strings would correspond to different particles, a bit like how a violin string can produce different musical notes depending on how it vibrates. An electron, a quark, a photon. In this picture, they're not distinct fundamental objects, but different notes played by the same kind of underlying string. Why does this matter for our story about time and time travel? Because string theory, in order to be mathematically consistent, requires that the universe have more dimensions than the 3% of space and 1 of time that we experience. Depending on the version of the theory, that could mean 10 dimensions or even 11 in certain extended formulations. The extra dimensions the theory suggests might be curled up unimaginably small, hidden from our everyday experience the way a distant tightrope looks like a one-dimensional line to someone far away, even though an ant walking on it would find it has real width and depth. These extra dimensions could, in principle, affect how gravity behaves, how space-time can be shaped, and even whether the sorts of shortcuts we call wormholes could actually be stabilized. String theory hasn't given us a working time machine blueprint, nothing close, but it has given physicists a richer mathematical language for asking whether shortcuts through space-time, closed loops in time, or exotic geometries are truly permitted by the deep laws of nature, or whether something about a full theory of quantum gravity will rule them out entirely. This remains one of the most exciting, unresolved threads in theoretical physics. Now let's take one more turn in our journey, because there's a question that often gets tangled up with time travel in the popular imagination, and that's the question of aliens. If time travel to the past were possible, and other technologically advanced civilizations have existed somewhere in this vast universe, wouldn't they have already visited us? This is a version of what's called the Fermi paradox, named after the physicist Enrico Fermi, who reportedly asked a version of the question over lunch with colleagues, given the sheer number of stars and potentially habitable planets in our galaxy alone, and given that the universe is old enough for advanced civilizations to have had plenty of time to spread out. Where is everybody? There are many proposed answers, and it's worth walking through a few because they connect beautifully to everything we've discussed. Perhaps advanced life is exceedingly rare because the specific sequence of chemical and evolutionary steps needed to produce intelligent technological beings is far less likely than we assume. This is sometimes framed in terms of a great filter, some improbable step in the evolution of life that most planets never manage to cross. Perhaps advanced civilizations are common but short-lived, destroying themselves or stagnating before they develop the ability to travel or communicate across interstellar distances. Or perhaps they exist, are plentiful, and simply haven't reached us yet because the distances between stars are so enormous and the speed of light is such an absolute cosmic speed limit that even a civilization capable of traveling at a meaningful fraction of light speed would still need centuries or millennia to cross between neighboring star systems. And this is where the connection to time travel becomes sharp and specific. If backward time travel truly is forbidden by the deep laws of physics, if wormholes can never be stabilized, if the paradoxes we discussed really do reflect something fundamentally inconsistent about traveling into your own past, then that would actually help explain why we've never had a confirmed visit from a future civilization, ours or anyone else's. No one has arrived from tomorrow, as far as we can tell. And if backward time travel is truly impossible, that absence of visitors makes complete sense. On the other hand, if backward time travel is possible but requires such staggering amounts of energy and control over exotic matter that only spectacularly advanced civilizations could achieve it, then perhaps no one nearby has crossed that threshold yet, or perhaps they have, and simply have reasons of their own for staying hidden, which is a much more speculative idea, straying from physics into pure conjecture. What I find most beautiful about this whole line of thinking is how it ties together threads that might otherwise seem unrelated. Time is not the fixed absolute backdrop that Newton imagined, but a flexible physical feature of the universe, woven together with space into a single fabric that can stretch, bend, and, perhaps under extraordinarily exotic conditions, even loop back on itself. That fabric came into being, along with everything else we know, in the hot, dense state we call the Big Bang, and the deepest attempts to understand its underlying structure, like string theory, keep pointing toward hidden dimensions and subtleties we're only beginning to grasp. And the question of whether we are alone in the universe turns out to be entangled with the question of whether time travel to the past is truly forbidden. Because a universe teeming with civilizations that could freely travel backward in time ought to look very different from the quiet, visitor-free universe we actually observe. So where does this leave us? Standing back on that beach, looking up at the stars? Time travel into the future is not speculation. It's confirmed physics already measured in satellites and particle accelerators, and it will only become more dramatic the closer we get to the speed of light or the stronger the gravity we can access. Time travel into the past remains a tantalizing possibility opened up by the mathematics of general relativity, riding on the strange back of wormholes and exotic matter, but it faces obstacles so severe, the instability of any tunnel through space-time, the demand for physically implausible negative energy, the deep paradoxes it seems to invite, that most physicists suspect nature has built in a kind of cosmic censorship. Some deep principle we don't yet fully understand that prevents time travel to the past from ever actually happening, even if the equations taken at face value don't outright forbid it. But here's the thing about frontiers like this one. The honest answer is that we don't yet know for certain. We have equations that permit strange possibilities, and we have deep principles, causality, the consistency of physical law, the yet unfinished project of unifying gravity with quantum mechanics that seem to push back against those possibilities. Somewhere in the tension between what the mathematics allows and what nature actually permits lies one of the great unresolved questions of fundamental physics. And that, to me, is what makes this such a thrilling place to stand as scientific explorers. Not because we have the final answer, but because the question itself, taken seriously, forces us to rethink what time even is, where it came from, and whether the universe we inhabit is even the only one there is. Whatever the ultimate answer turns out to be, the search for it will keep teaching us extraordinary things about the fabric of reality, and that, in the end, is a journey worth taking, regardless of which direction in time it leads us.